You tap a button and a face appears from another continent. The picture may cross your room by radio. It may leave your neighborhood through copper, but somewhere along the route, the signal will probably enter a thread of glass. That thread can pass beneath streets, across deserts, and through the deep ocean. The glass itself is about the width of a coarse human hair. Around it, layers of plastic, strength fibers, metal, and steel build a cable that can survive the route. Inside the cable, there is no tiny picture and no voice. There are pulses of light, shaped by machines at each end. They travel through glass that looks ordinary, yet is far purer than a window or drinking glass. This creates a strange material puzzle. Glass is brittle. Bend a window pane, and it breaks. Shine light through a thick block, and the beam fades. So how can a glass thread bend around a spool and carry a signal across a continent? The answer begins inside the glass. It leads through a hot draw tower, into a worldwide cable network, and down to the ocean floor. It also reveals a cost hidden by the idea that digital life is weightless. People guided light before they could send data through a long glass fiber. Water jets could carry light around a curve. Bundles of short glass fibers could illuminate a space or carry an image through a medical instrument. But seeing light follow a path was not the same as building a communication line. A useful line had to carry a clean signal for kilometers. It also had to survive pulling, bending, joining, weather, and years of service. Early glass lost too much light. Some loss came from imperfect surfaces and rough geometry. Much more came from the material itself. Ordinary glass contains traces of water, metals, and other ingredients that can absorb or scatter selected colors. Imagine trying to see through a stack of thousands of windows. Each pane may look clear across a room. Add enough panes, and their small losses become a wall. A long fiber creates the same problem continuously, one small distance after another. This left engineers with two possible conclusions. Perhaps glass had a natural limit that made long communication impossible, or perhaps the available glass was simply too dirty and too uneven to reveal what pure silica could do. In 1966, Charles Cow and George Hockham argued for the second answer. Their work showed that a carefully designed glass guide could support long-distance communication. The remaining loss, they argued, was not an unavoidable law of glass. That was a powerful change in the question. Instead of asking how to force more light through bad glass, researchers could ask how to make glass that had never existed at industrial scale. Even a perfect glass thread would not have created a network. It needed compact light sources, fast detectors, dependable joints, protective cables, and electronic equipment. Carriers also needed standards, money, routes, permits, and a reason to replace working systems. The material problem came first because every other improvement was wasted if the light vanished too soon. To understand how researchers reduced that loss, we need to open the thread itself. The main ingredient is fused silica. Its atoms form an amorphous network, meaning they connect without repeating in a crystal pattern. The network is solid and stable, but its small irregularities still affect passing light. At the center is the core. This is the region designed to carry most of the optical signal. It is not an empty tunnel, and it does not contain a hidden metal wire. Around the core is the cladding. It is also glass, usually based on silica, but its composition is adjusted differently. The boundary between these two glasses is the key to guidance. Light travels at different speeds in different materials. Refractive index is the number that describes that difference. The core has a slightly different index from the surrounding cladding, creating conditions that keep useful light patterns near the center. A common drawing shows a ray bouncing between two perfect walls. That picture helps at first, but it is incomplete. The boundary is not a mirror, and the light does not travel like a marble in a pipe. In a single-mode fiber, light travels as one allowed field pattern. Engineers call that pattern a mode. Part of it fills the core, and part extends into the cladding before fading away. This is why the visible core edge is not the whole story. Splicing two fibers requires their light patterns to meet closely. A tiny offset, dirty end face, or mismatched design can throw useful power away. As light moves forward, its power slowly falls. Attenuation means signal loss over distance. It changes with wavelength, glass quality, bends, joints, and the condition of the installed cable. Some loss is built into silica. infrared light can set atomic bonds vibrating. At the other end of the spectrum, ultraviolet absorption rises. Between those regions lies a broad window where the glass can be exceptionally clear. Another limit comes from frozen microscopic variations in the glass. Rayleigh scattering means light redirected by features much smaller than its wavelength. It is not ordinary dust floating inside the fiber. Unwanted traces add their own losses. Hydroxyl groups, which contain oxygen and hydrogen, absorb particular wavelengths. Tiny amounts of certain metals can also darken the path. Purity must therefore be chemical, not merely visual. Bending changes the guidance conditions. A gentle curve keeps the light pattern supported. A tighter curve lets more energy escape into the cladding and coating. The signal can weaken before the glass shows any visible damage. The glass remains brittle, so why can it wrap around a spool? The answer is scale. A thin strand bends with far less stretching at its outer surface than a thick rod bent around the same curve. Surface condition matters just as much. Freshly drawn glass can be remarkably strong because it begins with very small flaws. A polymer coating is applied immediately to protect that surface from scratches, moisture, and handling. Modern performance still needs a defined context. One current international standard covers a common class called G.652 single-mode fiber. It specifies geometry, strength tests, bending conditions, and loss limits at stated wavelengths. For one G.652 category, cabled fiber has a maximum specified loss of 0.30 decibels per kilometer across a narrow band near 1,550 nanometers. That is a standard limit, not the result for every installed link. The contrast with early glass is enormous. Yet the important point is not one record number. Low loss emerges from the entire chain: composition, purity, structure, drawing, coating, cabling, splicing, installation, wavelength, and maintenance. Once purity became the target, ordinary glass making was not enough. Melting a cleaner batch could not easily remove every troublesome trace. Researchers needed a process that built the glass from highly purified chemical ingredients. The central manufacturing object is a preform. A preform is a thick glass body containing a large version of the future fiber's radial structure. Its center and outer regions already hold the intended composition pattern. One process sends purified chemical vapors through a rotating silica tube. Heat makes glass-forming material collect in controlled layers. Other factories build material outside a support, or grow the preform along its axis. The exact method varies, but the logic stays similar. Start with ingredients that can be purified as chemicals. Deposit them without reintroducing contamination. Change the recipe across the radius to shape how the finished fiber guides light. The deposited material is then consolidated into dense glass. Water and unwanted residues must be controlled during this stage. A porous, cloudy body becomes a clear preform ready for the draw tower. At the tower, a furnace softens one end. Gravity and controlled pulling draw a continuous thread downward. Sensors watch the diameter, while the large core and cladding pattern shrinks into hair-scale geometry. The image can look like stretching taffy, but the control is far stricter. Small changes in temperature, tension, diameter, or composition can alter strength and optical behavior across kilometers of product. Before the new surface meets ordinary handling, liquid polymer surrounds it and cures. The coating does not carry the light. It preserves the surface that lets brittle glass survive later cabling and installation. In 1970, a Corning team crossed the widely cited threshold for low-loss communication fiber. Robert Maurer, Donald Keck, and Peter Schultz combined glass chemistry, waveguide design, drawing, and persistent measurement. That moment mattered, but it was not a finished internet cable. Early fibers still face loss, strength, coating, joining, production, and reliability problems. The famous sample was a doorway, not a deployed network. Commercial systems followed only after more work across many institutions. Semiconductor lasers had to last. Detectors had to respond quickly. Splices had to lose little light. Cables had to protect the fiber through pulling, weather, water, and repair. Field trials arrived in the late 1970s. Early commercial systems appeared around 1980, modest by modern standards but already useful. Later, fibers, wavelengths, amplifiers, and electronics pushed signals farther and packed more information into each route. The breakthrough was therefore a chain, not a single invention. A scientific argument made extreme purity worth pursuing. A manufacturing process made that purity repeatable. A wider engineering system made the glass trustworthy enough to bury and forget. Communication lines before fiber already crossed cities and oceans. Copper cables carried telephone calls. Microwave towers sent signals across land. Satellites linked distant regions. Fiber did not begin global communication from nothing. What it changed was a physical limit. Lower loss allowed longer distances before a weak signal needed help. Broad optical bandwidth also gave later systems room to carry many streams through one strand. Early links used machines that detected a fading signal and created a fresh copy. Each regeneration point needed equipment, power, space, and maintenance. Extending the distance between those points changed the economics of long routes. Later systems added optical amplifiers, which strengthened light without first turning every signal back into electricity. Engineers also sent different colors through the same fiber. Each color could carry its own stream of encoded information. None of that capacity belongs to glass alone. Lasers create the pulses, detectors read them. Electronics shape and correct the data. Software decides where it goes. Standards let equipment from different places work together. Civil works matter too. A fiber route needs ducts, poles, trenches, landing stations, buildings, power, access rights, and repair plans. In many projects, installing and protecting the route costs more effort than manufacturing the glass inside it. These systems gradually became the long-distance skeleton for telephone and internet traffic. They also connected mobile towers, data centers, research facilities, financial networks, and cloud services. Demand for computing pushed deployment, while new capacity encouraged more digital services. The ocean makes the scale visible. A deep water cable can look surprisingly narrow, but it remains far larger than its fibers. Near shore, extra steel armor protects against anchors, fishing, waves, and a rougher seabed. Along the route, repeaters restore optical power. A conductor within the cable feeds electricity to that equipment. Branching units divide paths. At each end, a landing station joins the ocean system to networks on land. In 2026, the International Telecommunication Union reported that submarine cables carry more than 99% of worldwide data traffic. That figure describes the international system, not the final connection to every home or phone. The same network that makes distance feel small can reveal geographic inequality. A major hub may have many separate routes. An island country may depend on only a few cables, sometimes approaching from similar directions. When one route breaks, traffic may shift elsewhere. When several fail, capacity can fall sharply. Repair depends on fault location, permits, weather, a suitable ship, spare cable, skilled crews, and access to the damaged section. This makes resilience more than a materials property. The glass may perform exactly as designed while the system remains vulnerable. Geography, investment, regulation, maintenance contracts, and route diversity determine who can recover quickly. Satellites and radio links remain essential, especially for remote access, mobility, and emergencies. Copper still works well over many short connections. These systems complement fiber, but they do not replace every high-capacity ocean or land route. The fairest historical claim is therefore bounded. Ultra-pure silica removed one major barrier to moving information over long distances. Civilization chose how widely, unevenly, and dependently to build around that new ability. A bare fiber seems almost weightless. That makes its environmental story easy to underestimate. The finished thread begins with chemical plants, purified ingredients, heated reactors, furnaces, draw towers, coatings, testing, and rejected material. A life cycle study of one vapor deposition process found that electricity and raw material choices could change the result substantially. That does not give every fiber one carbon number. Factories, grids, yields, recipes, and product grades differ. Then the system adds mass. A practical cable may contain several polymers, strength yarns, water barriers, metal conductors, and steel armor. Those layers keep the glass dry, aligned, unbroken, and repairable across a harsh route. Protection creates an end-of-life problem. Materials designed to remain together for decades do not separate easily. A cable can be technically recyclable while still being costly to collect, identify, open, sort, and process. Comparisons with copper sound simple but rarely are. Should we compare 1 kilogram, 1 kilometer, 1 data rate, or 1 lifetime of service? Each choice changes what appears efficient. One published cable study found no clear universal environmental winner between its copper and fiber cases. Another found that redesign could improve recovery for the fiber cable it examined. Both results depend on older, specific products and assumptions. Installation moves the boundary again. On land, crews open roads, pull cable through ducts, climb poles, and work around existing utilities. At sea, ships survey routes, lower cable, bury selected sections, and return when faults need repair. Seabed effects are not identical everywhere. A cable resting in deep, soft sediment differs from a buried shore landing through sensitive habitat. Route, burial method, water depth, repair frequency, and local ecology set the consequence. The human cost is also difficult to compress into one figure. High temperature and chemical production need industrial controls. Cable construction brings traffic, lifting, electrical, and excavation hazards. Ocean repair adds heavy machinery, weather, navigation, and long deployments. There is a quieter social cost in unequal backup. Places with few routes may wait longer or lose more service after damage. Education, banking, health systems, government work, and family communication can all share that physical bottleneck. None of these costs makes optical fiber a mistake. They show why the word digital can mislead. The signal may be light, but its path is made from factories, polymers, metals, ships, trenches, energy, ecosystems, and labor. Silica fiber is already close to important physical loss limits in its best operating window. That means the next improvement cannot come from purity alone. Better networks must work on several layers at once. Factories can reduce waste, improve yield, recover materials, and use cleaner electricity. Cable designers can reduce unnecessary material while preserving decades of service. Those goals can conflict because a lighter cable that fails early may save nothing. Longer life may be the most valuable material feature. Better coatings, water control, bend management, testing, and installation can protect existing routes. Repairable systems can keep a local fault from turning into full replacement. End-of-life design deserves attention before deployment. Clear material records and separable layers could improve recovery. Yet, a cable must still survive pulling, crushing, moisture, fire rules, animals, anchors, and the service conditions of its route. Network design can reduce human vulnerability. More diverse landings, shared repair resources, faster permits, compatible spares, and clear emergency coordination can matter as much as another small reduction in glass loss. Researchers are also developing fibers that guide light through air-filled structures. These designs may change delay, loss, power limits, or sensing. They are promising research paths, not inevitable replacements for the installed silica network. The crucial comparison will be complete and specific. A laboratory result must become manufacturable fiber, dependable cable, joinable routes, affordable equipment, accepted standards, and long service before it changes infrastructure. That is the lesson of silica itself. The material breakthrough was real, but its power appeared only after chemistry, manufacturing, electronics, construction, policy, and maintenance learned to work together. Return to that distant face on your screen. The image still feels immediate and almost weightless. Now the path behind it has thickness, a disordered glass network, a guided light pattern, a protected fiber, and a cable crossing the seabed. It also has a history. Researchers first had to believe the loss was removable. Factories then learned to build purity into a large preform and preserve it while drawing kilometers of fragile glass. The thread did not create the connected world by itself. People built sources, detectors, standards, routes, landing stations, ships, and institutions around its unusual behavior. Other people keep that system working when weather, anchors, earthquakes, or simple accidents break it. The internet can feel like a place without material. What else would gain weight if we opened it this way? Its long-distance body is glass, carrying light because a civilization learned to protect the thread.